Okay, so in this problem we've got an inclined plane, inclined at an angle theta, and we've got M1 on that plane, and we've got this pulley here and M2 hanging down here. And in part A, we're asked to write down an expression for the net force acting on M1. So we know that the net force is given by M1A. And in this case, we're told that M1 is moving up the slope. So the force pulling it up the slope is the tension in this string. So we've got the tension in the string. Now let's consider the other forces acting on our mass M1. We've got the weight force going down, so that's the mg, and we can split this weight force into components. So we've got the m1g sine theta pulling it down the slope, and then our normal force is going to be equal to m1g cos theta. So we've got the weight force pushing it down into the slope, and that causes this normal reaction force here. So we've got m1g sine theta pulling it down the slope, and then this reaction force results in the friction, so we've got minus mu k m1g cos theta, which is also pulling it down the slope, opposing its motion up the slope. Okay, so that's our answer to part A. For part B, we're asked to write a similar expression for mass 2. So with mass 2 over here, we've got m2g, which is pulling it down, its weight force, and then we've got our tension force, T2, pulling it up. So those are the only forces acting on this second mass, so it's a bit simpler. We can write m2a is equal to m2g, which is causing it to accelerate down, and then minus T2, which is pulling it up. Okay, now part C, we're now needing to write an equation for the net torque on our pulley here. So it's a disc with radius r and mass capital M. And so we've got the tension here. So this tension T2 is pulling it around this way, and tension T1 is pulling it around that way. So because it's moving this way, we know that T2 is bigger. So the net torque, we've got T2, which is acting at radius r, and then in the opposite direction we've got T1, which is also acting at radius r. And we know from Newton's second law for rotation that this is going to be equal to I alpha. So we've written down an expression to describe the net torque there. Now in part D, it asks us to combine these expressions to come up with acceleration. So the first two are fine, they've got acceleration, but we're going to need to work on this third one a little bit in order to get our acceleration. So we know that the moment of inertia of a disk is given by a half mr squared, and the alpha is related to the acceleration through a over r. So we can substitute these two expressions in here. So we've got the I, which is a half, so we've got I, which is a half mr squared times a on r is equal to, let's take r out as a common factor, r t2 minus t1. Now we can cancel some r's. We've got an r squared here, which we can cancel with that r, and then we've got an r on both sides, which cancel each other out. So we end up with a half ma is equal to t2 minus t1. And now we've got three equations, 1, 2, 3, which we can solve simultaneously in order to come up with our expression for A. So let's do 1 plus 2 plus 3. This tells us that m1a plus m2a plus a half ma is equal to t1 minus m1g sine theta minus mu k m1g cos theta plus m2g minus t2 plus t2 minus t1. So these tensions all cancel out, and we can pull the acceleration out as a common factor. So we have a times m1 plus m2 plus a half m is equal to m2g minus m1g sine theta minus mu k m1g cos theta. And so then we can rearrange this, and we have a is equal to m2g minus m1g sine theta minus mu k m1g cos theta, all divided by m1 plus m2 plus a half m. So we've now come up with our expression for acceleration. So if we were given numbers, we could substitute them in. Now in part E, it asks us how would this expression change if M1 was sliding down the inclined plane. Okay, so M1's now going down the plane, so everything's going this way. What's a bit different is that the friction force is then acting up the plane. So if we wanted to rewrite these expressions, we'd have M1A is equal to m1g sine theta's now the biggest force, which is pulling it down, but the friction is opposing this, so this is minus mu k m1g cos theta, and then the tension force is pulling it up. M2a, we've now got it's being pulled up, so T2 minus M2g, and our moment of inertia is also in the opposite direction, as now T1's bigger than T2. So we've got a half ma is equal to T1 minus T2. Then once again, we can sum all these together. So hopefully you can see we'll end up with a times m1 plus m2 plus a half capital M, and these will cancel, the t's will cancel, and we'll end up with m1g sine theta minus mu k m1g cos theta minus m2g. And so to get the acceleration, we just need to divide by this. So this will be over m1 plus m2 plus a half m, and we get rid of that from there because I divided by it instead. I just didn't want to write it all out again. So this is our new expression. So we may have expected that it would just be the negative of this acceleration as the acceleration has changed direction, but because the friction also changed the direction that it was acting, in the first case it was opposing the motion, so it was pulling it back down the slope. In the second case, it's still opposing the motion, but now to oppose the motion, it's pulling it up the slope. It's not quite the negative of this expression. We needed to flip the sign in front of the friction.